Hi guys, in this project I want to repurpose this tower fan as a wind turbine. I've already removed some parts, as you can see, some covers and a couple of other things. And next thing I'm going to remove is the rotor and the motor. The motor is fixed with these screws, which have to be removed first. And the rotor is also fixed with screws, with those two, and they have to be removed as well. Now I have removed the rotor. Here it is. Now I can continue with the motor. Now it's also removed, and I lay it aside. Perhaps it can be used again sometime. Now this is the place where the generator, a stepper motor, will be placed. Here are the parts I intend to use for the wind turbine. This is the stepper motor, a NEMA 17 stepper motor from NPOS, model number 17HS4401. And from there it goes to the bridge rectifiers, and I've taken some older ones from spare parts. And this is a B40 C3200 or 2200. And this means that it runs at 40 volts and up to 3.2 amps. And those two bridge rectifiers will go to these capacitors, and they have a capacity of 4,500 microfarads or 4.5 millifarads, and that's almost the maximum that is given in the data sheet of these rectifiers, which is 5 millifarads. And for the output voltage, I will use this LM25996 voltage regulator. It can be regulated to voltages from 35 volts to 1.5 volts. I'll put it to 5 volts, so I can, for example, charge batteries that are usually charged with 5 volts, and also perhaps run some devices with it. And it has an output of a maximum of 3 amps, which should be sufficient for all my needs. And this is the USB that I will later connect to the LM2596, so I can attach those battery chargers or USB devices. And this is an adapter that I will use on the stepper motor here to connect the two shafts of the stepper motor with the shaft of the rotator, which is 8 millimeters. And I will probably, or let's say I would like to avoid using this one, so I would have to destroy the motor. But if I don't find a proper shaft, 8 millimeter, I will have to use this one. Anyway, that's the parts that I will use. Perhaps some additional wires, of course, to finish the wind turbine. I forgot to mention, those capacitors will be used to smooth the output voltage of the rectifiers, so the voltage doesn't become so wavy and instead becomes more constant. I've just noticed something very convenient about the whole device, and that is that the mount on which the stepper motor will be placed fits exactly in the right way, so the motor and the rotator are right on each other, so there's no space in between. As you can see on the top, it's right in there, and on the bottom it fits exactly on the adapter. So that's very convenient. I don't have to use any spacers or something, I just have to attach the motor here. And then I will use for the second shaft that goes into the hole of the rotator, here's the screw where the shaft will be fixed. For that I will use this thing I've taken from a printer, which happens to have the exact value of the diameter it has to have. That is about 7.96 millimeters, which is the same as the diameter of the shaft of the original motor here. First have to grind some material away here, like here, so that the screw can be fixed firmly on the shaft. And that will be all. After that I can go to the electronics section. Okay, done. So this is the shaft that I will put in here and then into the rotator here. There we go. So as the stepper motor only outputs about 3 volts or a little bit more for each coil, I need to think of something that increases the voltage, the output voltage, because the LM2596 needs at least 6.5 volts to output 5 volts on the other side, and below that the 5 volts won't be reached. And so I have used two or a step up module like this, one for each coil behind the rectifier, to increase the voltage to 12 volts. You can adjust the voltage, the output voltage here, according to this chart on those two points. You have either to connect or disconnect A and B to reach a certain voltage, and those are connected to 12 volts. So when they output the voltage, the LM2596 receives 12 volts, and that's sufficient to output 5 volts. So solder everything together. I've chosen to connect them in parallel, so it gets the most amperage out of the modules, and this will then later on power some battery chargers or other USB devices. As a small test now, I show that this module outputs 12 volts when I rotate the rotator here. So let's see, it's already at, there we go, 12 volts. I'm rotating relatively slow, so it doesn't reach 12 volts all the time. As you can see, there's a LED, an LED indicator. That one also consumes some current, so I will probably remove the LED on both modules, as well as on the LM2596. Altogether, that will certainly make about 50 to 60 milliamps that can be saved just by removing the LEDs. I have now finished most of the soldering with the LM2596 connected to the crocodile clamps of the multimeter, and the LM2596 goes to the two parallel 12 volt modules, which go to the two capacitors of 4.5 millifarads, which go to the bridge rectifiers, which go to the stepper motor. And this stepper motor will now be rotated, and then the multimeter should show 5 volt at the output of the LM2596. Let's see. Yes, that's 5 volts. So now let's measure the current that goes through the LM2596 output. And therefore I will plug this one. I'll first rotate this to 10 amps. And this one here, so we can see this. Let's see. Of course, this only shows momentary values, and they peak somewhere around 250 milliamps. So that's not very much, but I'm optimistic that the wind will rotate the rotator much faster, and so the output will be a little bit higher, so that the overall power output is acceptable. According to the weather forecast, there's going to be a storm in a couple of days, so I had to hurry up a little bit and fix everything and put everything in place. Here I've glued all the parts and wires to the cover of the wind turbine so that nothing can move around anymore. Same for the motor, for the stepper. It's all fixed with screws, and the rest was already ready. And in addition, I've attached a revolution counter I've recently built, the other video, that will count the revolutions of the rotor, and then I can make a chart where you can see the RPMs corresponding to the respective power. And I'm hoping that this thing here will rotate at relatively slow speeds of the wind, and of course when there's storm that it will rotate really fast, and that the power output will be something that can be used, for example, for charging batteries, etc. Alright, now perhaps I'll make a cover stir here, so it's everything protected from rain or something, and well, then let's hope that the storm will come. So this is how I measure the RPMs now. I have replaced the needle by a segmented circle which has about 32 lines, and which will therefore increase the accuracy by 32 times. So I've put the RPM counter here, and I've glued everything together so it holds, at least for the time where I make the measurements. I know it doesn't look very nice, but I think it will hold in place. And as you can see, there's the fog light barrier and the segmented circle. I've taken that circle from a motor from a scanner. It's often found in scanners, so if you look for one, then you can find one there. The motor had to be sacrificed though to get this thing out of it, but it serves a good purpose, so no matter what. Now let's test the revolution counter. Its lowest RPM will now be 1.88. So if I rotate this very slowly, it should show that value. There we go. Now going a little bit faster. 37, that's about 30 revolutions per minute. Now that's 60 revolutions per minute, which corresponds to 1 revolution per second. And this increased accuracy will later on help to produce a chart for the power output versus the RPM. I guess that will be some kind of E function or exponential function, but we will see that later on when the storm begins and I take the measurement series. Right in the right place where the big wind turbines are standing. The voltage that's necessary is already reached. It's rotating, it's very nice. And now the wind is going a little bit slow. It's not 50 PS. Let's come back. Yes. About 4 revolutions per second, it reaches 5 revolutions. just an experiment. So I've now made a measurement in the storm, and the wind speed was, according to the weather forecast, around up to 40 kilometers an hour. And the maximum output that I got from the USB, that is directly where the load is, was around 400 milliamps at a voltage of 5 volts. So the overall output maximum was 2 watts. It turns out that the RPMs, the corresponding RPMs, are probably not very useful, because they ranged from around 300 RPM to 550 RPM at the same current. I think that's due to the fact that there are some capacitors in between, and they charge and discharge, and so there is a time lag between the measurement and the actual current. And so I think I will do another measurement series with hand drill and at constant RPMs, so the values will be more reliable to make a chart for the whole thing. I've also added a cover now for the front, so this is more or less rain protected. Now I'm going to attempt a measurement with this hand drilling machine on the side, which is directly attached to the shaft of the rotor. On the left we are measuring the amps, and on the right, or in the middle, that's the RPM. So let's give it a try. Again at around 120 RPM, no count yet. Let's increase RPM, there we have some count. Pretty constant at around 30 milliamps, and let's increase the speed. Alright, 240 corresponds to 240 milliamps, that's nice. Now 300, going to 300 RPM. And let's 260 milliamps. Let's go in the circle. 420, 400 milliamps. 280. 540, 600 RPM, 430 milliamps. We go in the circle, 1560, 720, 1140. We have 450 milliamps. It doesn't go any further. Okay. Seems like there's a maximum of 450 milliamps. That may be due to the step-up converters. I don't know. I had originally tried with one step-up converter, and that was also limited somehow to a certain current. Then I put two of them in parallel, and that would yield more output. So maybe if one attaches more of them in parallel, so perhaps 3, 4, 5, etc., maybe then the output will be higher. I don't know. So I've plotted here the characteristic curve of the circuit of the wind turbine with the values that I measured during the test with the hand drilling machine. And we had a maximum of around 450 milliamps, which will be reached at around, say, 900 RPM. And afterwards, that value cannot be increased anymore. So no matter how fast the wind turbine rotates, it doesn't change the value of the current anymore. So the power output stays the same after that value. And you can see in the curve there we have a 5 volt limit. That's the 5 volt limit of the LM2596 module. Only at a certain RPM, at around 240 RPM, the 5 volts are reached, and after that point the voltage stays the same, stays constant. And I guess that this is the reason why we have a jump here at around 240 RPM of the current from 79 to 240, and afterwards the current increases normally. Because before that the voltage is lower, and for some reason the current is lower as well. In the beginning, of course, there is no current, so I think that the curve is only relevant after this point. This configuration of the curve is due to the approximation, which is done by splines, and that's this part here is typical for splines. It's a kind of x to the power of 3 curve, and I think that the more likely curve would be along here, along this line, so it's more smooth, like this. Overall, I would say that this maximum of 450 milliamps is certainly not very high, but on the other hand, in the storm we had already around 400 milliamps. It was around here, at around between 400 to 500 RPM, and the winds are not blowing much faster anyway, usually, so I guess that the wind turbine is still of use in this size, because it won't reach such high values anyway. So RPMs of over 1000, certainly not. Those are only reached with the hand drilling machine in a test. So my conclusion is that the wind turbine can be used, but only in places where the wind is rather strong. That is, it should be in a high place, on the roof, or somewhere where there are no walls around. So on a plain where there's a lot of field around it, area around it, where there's no houses and no other obstacles. And on the ground, behind walls, it makes not much sense to use it, because it won't rotate at lower speeds of the wind. But if you use such a thing, then again, put it in a high position, or in a position where there's no obstacles around, and then you can output perhaps around 2 watts, by which you can load perhaps some lithium-ion batteries, 18,600 batteries or so, and well, some USB devices, smaller USB devices, perhaps an Arduino or something like that could be powered. But well, the bigger the better, I would say, in this case. That is such a wind turbine. Certainly, if you increase the size of it, you will get much more power out of it. And also crucial for this whole circuit was the stepper motor, which is a NEMA 17 stepper motor, and this stepper motor is rather small, and so there's a limitation by this motor anyway. And as a generator, I would rather recommend a stepper motor with more power output, or even a real generator. Otherwise, it's only useful for small devices. Okay, this was my presentation of the construction and testing of this wind turbine. It's rather a proof of concept than a really useful tool. Well, perhaps I'm going to charge some batteries with it, but certainly that's not my power generator of choice. Anyway, if you want to build something better, this shows that it can be done using a bigger generator or a bigger stepper motor, a larger rotator, or even some propeller type. And with the right materials, with the right configuration, you can certainly yield much higher outputs. And well, perhaps in the future I'm going to build something bigger, I don't know. But for now, if you liked the video, give a thumbs up, feel free to comment and perhaps even subscribe. I would be very happy about that. So, until next time, bye!